All right, today we're pulling back the curtain on one of engineering's biggest secret weapons. Seriously, it's a mathematical trick that takes these ridiculously complex problems and turns them into something you could solve like on the back of a napkin. We are talking about the Laplace transform. Think about it. The suspension in your car, the power grid keeping the lights on, the control systems in a jumbo jet. We're surrounded by these incredibly complex dynamic systems. So the big question is, how do engineers even begin to predict what they're going to do? How do they make sure they're stable and maybe most importantly, safe?
Well, when you get right down to it, there are really two ways to tackle this. On one hand, you've got the hard way, wrestling with these just messy differential equations that describe how things change over time. It's a real headache. But then there's the smart way, clean, beautiful, simple algebra. The whole trick, the entire game, is figuring out how to get from that messy calculus world over to the clean algebra world.
See ya. Calculus versus algebra. See, if you want to describe the physics of just about anything in the real world, a moving car, an electrical circuit, you name it, you almost always end up stuck with these gnarly equations involving rates of change. In other words, calculus. And trust me, solving those things directly, it can be an absolute nightmare. Sometimes it's just plain impossible.
Okay, let's dive in. Welcome to the S domain. This is the engineer's power tool. This is where our secret weapon finally comes into play, the Laplace transform. Think of it like a mathematical portal. It lets us jump from the world we know, the time domain, into this new, much friendlier place called the S domain. And the best part? In the S domain, all that scary calculus just whoosh, becomes simple algebra.
And this image here shows the whole process perfectly. I mean, look at this. On the left, that's the hard road, right? Trying to solve the problem directly in the time domain. But check out the path on the right. We take our problem, we zap it with the Laplace transform to jump into the S domain. Over there, we solve a super simple algebra problem. Then, we just use the inverse Laplace transform to jump right back with the answer. It's this brilliant, elegant shortcut that saves an unbelievable amount of work.
So you're probably wondering, what is this mysterious S in the S domain anyway? Well, this quote here gets right to the heart of it. You might have heard of the Fourier transform, which breaks signals down into simple sine waves. Laplace is kind of like its more powerful cousin. See, S is what we call a complex frequency. It's made of two parts. S equals alpha plus j omega. Now that omega part, that's just your standard frequency, how fast something oscillates. But the really cool part is alpha. That represents growth or decay, the damping. It lets us analyze not just things that wiggle, but things that grow out of control or fizzle out over time.
Okay, so now we're getting to the really cool part, the system's DNA. Reading the blueprint. Because when we go into the S domain, we're not just making the math easier. We're actually getting a peek under the hood at the system's fundamental characteristics, what you could call its operational DNA. And the key to all of this is something called the transfer function, or H of S. It's actually a pretty simple idea. It's just the ratio of the system's output to its input, all in the S domain. But this one little function, it's everything. It's the system's unique blueprint. If you have H of S, you can figure out how the system will react to literally any input you throw at it.
Now, this blueprint is written in a special language, the language of poles and zeros. Just think of the transfer function as a big fraction. Poles are the special values of S that would make the bottom part, the denominator, go to zero. And that's a huge deal. They're the ones that tell you about the system's natural behavior, and most importantly, whether it's going to be stable or not. Then you have zeros. They're the values that make the top part, the numerator, go to zero. They can do things like block certain frequencies or change how the system responds to different inputs.
And this right here, this is where it all comes together visually. This is the S-plane, and it's basically a map of a system's future. It's so cool. See those X's? Those are the poles. If all of your system's poles are on the left side of that vertical line, the left half plane, congratulations, your system is stable. It'll settle down over time. But if even one of those poles wanders over to the right side, you've got an unstable system. Its response is going to grow and grow, probably until something breaks. It's a crystal clear life or death test for any design.
All right, theory is one thing, but let's see how this stuff actually works in the real world. A system in action, a step-by-step walkthrough. We're going to take an actual example and see this whole process from start to finish.
It's a simple three-step dance. Step 1, we model the physical system with a differential equation. Step 2, we transform it all into the S domain and solve it with easy algebra. And step 3, we inverse transform it back to the time domain to see what happens. Model, transform, inverse transform. That's it.
So here's our guinea pig, a simple mass hooked up to a spring and a damper. Classic physics problem. And that equation down there, that's the differential equation that describes its motion over time. Just looking at it, you can tell that trying to solve that thing directly for x of t, yeah, that would be a ton of calculus. Not fun.
But now, watch the magic happen. We take that entire messy equation and hit it with the Laplace transform. All those complicated derivatives just turn into simple multiplication by s. And just like that, poof, the calculus is gone. What we're left with is a simple algebraic equation that we can easily shuffle around to solve for the position, x of s. Seriously, the hard part is already done.
Okay, before we jump back to the time domain, there's one little cleanup step. Our solution for x of s is still one big, chunky fraction, so we use a handy technique called partial fraction expansion to break it apart. It's like taking a complex Lego model and breaking it down into individual, simple bricks. Each of those simple little pieces is something we know how to deal with.
And this brings us to the home stretch. Step 3. We take each of those simple little bricks we just made and we look them up in a standard Laplace transform table. It's basically a cheat sheet. For each simple piece in the S domain, the table tells us its partner back in the time domain. We just find all the partners, add them back together, and bam, we have our final equation for the motion over time, x of t.
So, we did all that math. What's the payoff? Let's go from the blueprint to reality and see the result. We started with the physical object, took a trip through the S domain, and came back with the final equation. So, what does that equation actually show us?
And here it is. This is the payoff. We plot that final equation, x of t, and we get this beautiful graph. It's a perfect prediction of how that mass spring damper is going to behave. You can see exactly how it's going to oscillate and how that damper makes it slowly settle down to a stop. We have a complete picture of its future, all because we took that little shortcut through the S domain.
And that's really the heart of it, right? From circuits to control systems, the Laplace transform turns what looks like impossible calculus into algebra you can actually solve. This isn't just for some block on a spring. We're talking about designing audio filters, keeping the power grid stable, building flight controls for rockets. The Laplace transform is the key that lets engineers translate the language of physics, which is calculus, into the language of solutions, which is algebra.
So it makes you wonder, right? What hidden behaviors could we uncover if we knew the DNA of the systems all around us? The transfer function gives us that blueprint for any system, showing us its deepest secrets about stability and behavior. What else could we predict? What could we build if we could read the hidden blueprints of everything that makes our world tick?